Okay, let's jump straight into this reading. I'm up at a ranch, if you must know, sitting by the fire. We're still on Section 1, Theory of Heat, Unit 3, Refrigeration and Refrigerants. Pure water boils at 212 degrees Fahrenheit at sea level when the barometric pressure is at the standard value of 29.92 inches Hg. This condition exerts an atmospheric pressure of 14.696 psia, 0 psig, on the water's surface. This reference point is on the last line of the table in Figure 3.7. Figure 3.7, the boiling point of water, the temperature at which water will boil at a specific pressure, can be found on the temperature pressure chart for water. Also see Figure 3.8. Water boils at 212 degrees Fahrenheit when the atmospheric pressure is 29.92 inches Hg, which shows the container of water boiling at 212 degrees Fahrenheit while at sea level and atmospheric pressure. When this same pan of water is taken to a mountaintop, the boiling point changes. Figure 3.9. Water boils at 203 degrees Fahrenheit when the atmospheric pressure is 24.92 inches Hg. 5,000 feet above sea level, atmospheric pressure 24.92 inches Hg, water boils at 203 degrees Fahrenheit. Because the thinner atmosphere causes a reduction in pressure, about 1 inch Hg per 1,000 feet. In Denver, Colorado, for example, which is about 5,000 feet above sea level, the atmospheric pressure is approximately 25 inches Hg. Water boils at 203.4 degrees Fahrenheit at that pressure. This makes cooking some foods more difficult because they now need more time to cook. But by placing the food in a closed container that can be pressurized, such as a pressure cooker, and allowing the pressure to go up to about 15 psi above atmosphere, or 30 psia, the boiling point can be raised to 250 degrees Fahrenheit. Let's see Figure 3.10. 3.10. The water in the pressure cooker boils at 250 degrees Fahrenheit. As heat is added, the water boils into a vapor. Since the vapor cannot escape, the vapor pressure in the pressure cooker rises to 15 psig. The water boils at a temperature that is higher than 212 degrees Fahrenheit because the pressure in the vessel has risen to the level that is above atmospheric pressure. Studying the water temperature/pressure table reveals that whenever the pressure is increased, the boiling temperature increases, and that whenever the pressure is reduced, the boiling temperature is reduced. If water were boiled at a temperature low enough to absorb heat from a room, the result would be comfort cooling, air conditioning. Suppose we place a thermometer in a pan of pure water at room temperature, 70 degrees Fahrenheit. Put the pan inside a bell jar with a barometer and start the vacuum pump. When the pressure in the jar reaches the pressure that corresponds to the boiling point of water at 70 degrees Fahrenheit, the water will start to boil and vaporize. This point is 0.739 inches Hg, or 0.363 psia. Figure 3.11 illustrates the container in the bell jar. The data can be found in the table in Figure 3.7. So this is 3.11. The pressure in the bell jar is reduced to 0.739 inches Hg. The boiling temperature of the water is reduced to 70 degrees Fahrenheit because the pressure is 0.739 inches Hg, which is 0.363 psia. Notice in figure 3.7 that the temperatures are listed in the left-hand column. So this is 3.7, the boiling point of water. The temperature at which water will boil at a specific pressure can be found on the temperature pressure chart for water. So, yeah, the temperatures are listed in the left-hand column and the pressures are found in the body of the chart. Hence the name temperature pressure chart or table. Sometimes, however, the information is presented differently. On some charts, the pressures are located in the left-hand column and the temperatures are found in the body of the chart. These charts or tables are referred to as a pressure temperature chart. Although the information is the same, the way that it is presented is different. Make certain that you know which type of chart you are using, or inaccurate calculations and system conclusions may result. If we were to lower the pressure in the bell jar to correspond to a temperature of 40 degrees Fahrenheit, this new pressure of 0.248 inches Hg, which is 0.122 psia, will cause the water to boil at 40 degrees Fahrenheit. The water is not hot even though it is boiling. The thermometer in the pan indicates this. If we opened the jar to the atmosphere, we would find that the water to be cold. Also, the pressure in the jar would rise and the boiling process would stop. Now let us circulate this water boiling at 40 degrees Fahrenheit through a cooling coil. If room air were passed over it, it would absorb heat from the room air. Because this air is giving up heat to the coil, the air leaving the coil is cold. Figure 3.12 illustrates the cooling coil. 3.12, the water is boiling at 40 degrees Fahrenheit because the pressure is 0.122 psia or 0.248 inches Hg. The room air is 75 degrees Fahrenheit and gives up heat to the 40 degree Fahrenheit coil. When water is used in this way, it is called a refrigerant. A refrigerant is a substance that can be changed readily to a vapor by boiling it and then changed back into a liquid by condensing it. The refrigerant must be able to make this change repeatedly without altering its characteristics. In addition, a good refrigerant is able to absorb and reject large amounts of heat as it transitions between the liquid and vapor states. Water is not normally used as a refrigerant in small applications for reasons that will be discussed later. We used it in this example because most people are familiar with its characteristics. To explore how a real refrigeration system works, we will use refrigerant R410A in the following examples because it is commonly used in residential air conditioning. See figure 3.13 for the temperature pressure relationship chart for several. Okay, we're left on a cliffhanger because that's on the next page. Anyways, that was a pretty quick one. Pages 44 and 45. See you guys tomorrow.